Hi everyone, I'm Jaewoong from South Korea. I'm a GDE for Android and Kotlin and currently working at Stream as an Android developer advocate. Today I will be speaking about becoming an Android librarian based on my open source contribution experience. Before diving into the details, I'd like to elaborate on my open source contributions. I have created and published over 80 open source projects and libraries on GitHub, mostly about Android and Kotlin, such as Balloon, Landscapist, Sandwich, and Pokédex. Luckily, my open source libraries have been used by many products, including Twitter, PayPal, Wikipedia, Other, and many other global applications for Android, and by millions of global end users across millions of different Android applications. And let's talk about open source life cycles. I treat open source software as a product for developers, like we normally build applications in our daily life as developers. So we should maintain open source libraries systematically from start to end to make them successful. For this, it would be great if you have a dedicated project lifecycle to manage open source projects. But in this talk, I'm going to introduce an open source lifecycles I have used for around 5 years. The first phase is design. Software design is one of the essential phases in the lifecycle, especially in API development, because we need to think about the importance of the problem we want to solve, and we should draw the comprehensive structure of public interfaces. In other words, we should think about the market needs and how the product will be used by developers. Normally, I follow these steps in the design phase. Firstly, I define a problem and make clear what I really want to solve in my project, and I start to research how to solve the problem to make sure my approach makes sense. Next, if I have verified the feasibility of my approaches, then I make sure the dependencies between each module and which other dependencies are required. Lastly, I convert my approaches into blueprints about architecture and API structures, and start to design detailed specifications such as inheritance between interfaces and classes, and define API surfaces based on blueprints. This phase may be boring to someone because if you have finalized these design phases in advance, you can reduce many resources about thinking of API structures in your subsequent steps. The next phase is development, which is implementing the details such as classes, methods, extensions, and everything you need to build your library. In this phase, there are many strategies to make your library stable. The first one is minimizing API surfaces. Let's assume there is a module which includes public interfaces. In this case, we exposed the entire API, so external clients can access and depend on the entire API. So what if we change or remove the public interface in the new release? Then clients will face code breaking and it will bring the build failure. As a result, clients need additional resources for migrating to a new release of your library. And let's assume again, only the orange ones are exposed to the outside, and the blue ones are not allowed to be accessed from outside. Due to we restricted the API accessibilities, clients can only access and depend on the orange ones. So if you change or update the internal APIs, or if you expand more features and restructure internal APIs, the external clients will not be affected. So this allows API maintainers to maintain the APIs much easier, and clients can reduce many resources for migrating to new releases. To minimize the API surfaces as much as possible, we should think about the visibility modifiers. In Kotlin, if we don't clarify the visibility modifier, the default visibility is public. So that means external clients can access and depend on the interfaces without restrictions. So let's see an example of a random class. As you can see, if we don't clarify the visibility modifier, library users can access to the class. So if you designed the APIs are supposed to be used internally, you must explicitly attach visibility modifiers such as internal or private to prevent unintended behavior from the user side. Especially in the case of extensions, APIs can be exposed much easier because they are widely applied in the project. So it's important to attach an internal modifier and restrict accessibility to the extensions if you don't want to expose the extensions to entire user projects. But if you are also targeting Java developers, you should give a heads up for the internal modifier. As you can see on the right side, extensions are compiled into Java bytecode with the public final static keywords, so they are still accessible from Java projects. If you want to prevent accessing from Java project, you should attach JVM syntactic annotation to your internal methods or properties. Then, as you can see on the right side, they will be compiled into Java bytecode with a syntactic keyword, and they can't be accessed from Java projects. However, as your project grows, managing entire API's visibility modifiers is difficult. In this case, we can use explicit API mode. The explicit API mode throws errors or warnings if you don't clarify visibility modifiers to your interfaces. You can enable the explicit API mode by adding the code block on your Gradle file. After enabling the explicit API mode, you can see entire classes, properties, and the functions will get errors if they don't have visibility modifiers. So they force you to attach visibility modifiers, and it prevents missing some visibility modifiers in your project. But it can be very hard if you try to apply the explicit API mode in a large project at once. So you can enable the explicit API warning mode and migrate it gradually. And next, I would introduce a Gradle plugin to manage public APIs, which is Binary Compatibility Validator by JetBrains. This plugin helps you to track and manage exposed API changes, so you can double-check whether you make any mistakes. To use this plugin, add the plugin on your Gradle files and run the command line on your terminal. Then the plugin will generate the entire specifications of your public APIs in a file called module.api. So if there are any changes on your public APIs, you can double-check and ensure which API was changed by comparing it with the previous file. Google also uses a similar tool called MetaLava to generate metadata of APIs. If you're interested in the tool, you can look around it on the AOSP website. And next, let's talk about Android resources. If you build a library, the library will be packaged into AAR file, which includes many Android resources. Normally, AAR file includes layout, Java, and all Android value resources, such as strings, colors, and styles by default, and they are delivered to library users. For example, if a library includes color value in the colors.xml file, then library users can access and use the color values without restrictions. So here is a problem. If library maintainers remove the resources when they don't need the colors anymore, then library users will encounter a compilation error when they update to a new release of the library. And it's very difficult to debug because the library users never know which libraries include what resources. So I would introduce a public tag to manage exposed resources. You can specify what resources should be exposed or not by defining public tags in a public.xml file. So you can selectively mark what resources can be accessed by users, and the other resources will be marked as private automatically. So even if you add only one public tag for a resource, all other resources will be marked as private. As a result, if you compile your library, the public.xml file will be included in the AAR file and it will be delivered to user projects. Let's see an example. If you don't restrict any resources with the public tag, as you can see, the library users can access and use the resource in their project. But if you mark specific resources with the public tag, then for other resources, Android Studio will not support the auto-completion, and if users type the resource by manually, they will get a lint error on their IDE. So how this works? It's because Android Studio includes built-in lint check tools by default, and you don't need to do an additional setup. About the exposing Android resources, I'm going to share one of my open source experiences. There is an open source library called Balloon, which allows you to build tooltips for Android. Fundamentally, the Balloon uses a layout file called layout_balloon.xml to implement the body of the tooltips. And users also can customize the body of the tooltips by using their own layout file. One day, someone reported issues about the library, but it was very difficult to reproduce, and the crash report was not helpful at all. So I requested the code snippet of the builder class, and I found something interesting. They used a custom layout called the layout_balloon.xml file, which is the same name as the library's one. So what happens if a library user uses a resource that has the same name with the library's one? As you may expect, a user project overwrites the library's resources, and the library will use the overwritten one. Here is a problem. So resource overwriting is very difficult to debug, which means even if you deep dive into crash messages. So how can we prevent resource overwriting? For this, I'm going to introduce resource prefix. Resource prefix is forcing a naming convention for your resources, so maintainers will not make mistakes, and library users can know the origin of resources. You can enable the resource prefix by defining your naming convention in the Gradle file. Normally, I use my library name underscore for the prefix. Let's see an example. After enabling the resource prefix, you will get a lot of lint errors on your IDE because the resource names are not following the convention. By using resource prefix, you can take a different pattern than the resource naming conventions commonly used in user projects, so you can prevent misuse and reduce user confusion. Next, let's talk about the R class. The R class is the dynamically generated class to identify entire assets, and it's kind of a fundamental concept in managing Android resources since Android was born. The R class sometimes reminds me of the Eclipse, maybe around 7 to 8 years ago, but now we don't have any chance to see the R class directly in the Android Studio because it has been hidden. I found a very ancient image like 6 to 7 years ago, which is the internal structure of the R class. As you can see, the R class defines R unique IDs for Android resources, and entire Android modules have a dedicated R class. I want to show you how the R class is transferred between dependent modules. Let's see an example step by step. The M module depends on the library module, and the library module depends on the Google's material design module. If you build the project, the material module will generate its R class, and the R class includes entire definitions of the Android resources about material design. And now, we need to pay attention to this. If you build the library module, not only the R class will generate ID fields about the library module, but also it will generate entire ID fields about the material modules as well. Likewise, for the M module, when creating an R class for the M module, entire ID fields in the library module will be transferred into the M module's R class. Therefore, a very large R class will be created at the end. So we can call this transitive dependency. Even if the app module does not depend on the material library directly, entire ID fields in the material module's R class are transferred to the M module's R class. So I unpacked the AAR files and of the library module to show you how the dependencies can be transferred. The library module only depends on the material library and doesn't include any kinds of Android resources. But as you can see, the library's R class includes a lot of resources classes. So if you open one of them, you will see there are a lot of ID fields declared. As a result, when you build the project, it's like creating more than 1,000 to 10,000 of lines of code, many times by duplicating them between modules. And in reality, we normally use a lot of dependencies with multi-module structures, so it will be much bigger. That's why we used to encounter 64K multi-dex limitation issues when we build our project, even if we don't use many libraries. It's because the Dalvik executable files limits to total number of methods that can be referenced within a single dex file to around 65K methods, including Android frameworks and your own code. For this, Jake Watson already pointed out that and suggested a way to prevent references from transitive dependencies being included in library R files, which is enabling the non-transitive R class option on your Gradle file. You can enable the option by adding the code directly to Gradle.properties file or using the refactor menu on your Android Studio. After enabling the option, the R classes will not be transferred into dependent modules, and the subsequent modules will have only references to that R classes. This avoids generating a significant amount of code when you build your project, and you can also expect to reduce build time. Let's see an example. In the left image, user project includes our unrelated resources, including material design, which means your library project is using third-party libraries, and those third-party libraries or classes are transferred into the user project through your library. But if you enable the non-transitive R class option, like the right side image, as you can see, your library does not include other libraries' resources anymore, and users can only access your library resources with the full name package. So I calculated how much improvement actually we can expect. But please note that there is a tolerance because I tested with my library balloon. So as you can see, if there are 10,000 end users of your library, you may prevent waste of around 115 megabytes of storage. And for 1 million, it will save 10 gigabytes of storage. For 10 million, 1 terabyte of storage in the world somewhere, and so on. And the non-transitive R-class option might be very useful for application developers as well, who build their project with multi-modules features. But if you enable this option, you may encounter the unresolved reference error. For this, you should change it to full name package, and you can also rename the package name by importing with namespacing. Then it will look more clean on your code than the full name package. And next phase is preparing additional resources, such as documentation for library users. Normally, I invest a lot of time to provide good documentation. In particular, I try to comment on R elements that can be accessed externally, such as classes, properties, extensions, and methods, so that users can understand the functionalities without reading the codebase or the README page. In the case of commands, I am following the kdoc syntax provided by JetBrains. And I would introduce a documentation engine Docker, which JetBrains provide. By attaching the Docker plugin and typing a single command line, a web page is created to explore the entire specifications of the API based on kdocs. So users can search entire code specifications without opening their IDE. You can also provide a great developer experience to library users. And next one is the README file. I treat an open source library as a product for developers, and the README file as a product manual. So I normally try to write the README file as detailed as possible. Sometimes I used to invest time that is not much different from the cost of software development, because well-documented libraries can reduce a ton of resources from the user side. And let's talk about the release. The first one is Apache Maven. Apache Maven is a build automation tool which allows developers to connect many kinds of repositories like the source of truth. For example, uploading open source libraries to a specific repository, or searching and downloading desired libraries that developers want to import. There are 3 primary repositories. The first one is Sonatype's Maven Center repository, and the second one is JCenter, which was very popular among library developers, but unfortunately, JCenter shut down their service last year, and Google has their own Maven repository. You can publish your library on Maven Center, but the entire process is very tricky, such as getting approval from Sonatype and GPG key signing and many additional steps about validations. So if you're interested in publishing your library to Maven Central repository, you can check out Martin Braun's Publishing Android Libraries to Maven Central in 2021. And if you feel pressure publishing your library to Maven Central, there is an alternative, Jetpack. Jetpack uses a GitHub repository as a remote repository to build code and provide them in binary format. You can publish your library very easily, almost without setup cost. And the next phase is verification. Open source means more than just opening your code in public spaces. After releasing your library, it's not the end, it's just getting started. You need to continuously verify how the solution works, is valuable, and is efficient by communicating with library users. For me, I am joining many communities such as GitHub, Twitter, and LinkedIn for making many chances to communicate with developers and sharing my solutions with the community. So I can also have discussions with people and hear many feedbacks from their real-world experiences. It helps me find many corner cases that I have missed, and it solidifies the open source libraries. One of the great strategies to share your solution with the community is writing blog posts. You can make a good selling point by providing some solutions to the pain points in many ways, such as how to solve common problems in a nice way using your library. And building a sample project using your library is another great way to verify and market your solutions to the community. Sometimes a few lines of code are far more persuasive than words. If you want to read more about some tips for building your open source library, check out the post about becoming a successful open source librarian. If you have any questions or feedback, or if I was wrong, please feel free to reach out to me with these contacts. Thank you so much for your time today, and I am happy to talk about my open source experience.